this project, we used the design made in AutoCAD Inventor and established simulation in CFD Star. The behavior of the pump was simulated using 2 different programs.
With this in mind, water, oil, and 8 fluids with different values of density and viscosity were simulated. The simulation in MATLAB was carried out based on the algorithm from the Hydraulic Institute, taking as reference the data obtained for water regarding volumetric flow, head, and efficiency.
For the simulation in CFD, we have to make some assumptions. The first one was that all the fluids we're going to simulate were liquid. Also, because of their incompressibility, we made the constant density and segregated flow. We calculated the Reynolds number, and they were turbulent. Also, we assumed gravity to orientate the pump. And finally, we assume a steady flow because the idea of the pump is not to have accumulation inside of it.
After having the assumptions done, we continue with the selection of the models. In first place, we select all Bulla plus because it was hard to predict exactly the accuracy of the mesh, noticing that there were some cells with low quality. After, we use K omega for the simulation of the oil because it can comprehend fluids with a greater viscosity, and we left K epsilon for water because it is a less robust model and it can accrue well. Finally, we use Reynolds average Navier-Stokes.
In general, the results show that in all cases, as the volumetric flow increases, the efficiency increases up to a point of maximum efficiency and then decreases. Furthermore, it can be seen that the fluids with a higher efficiency are 1, 6, and water, and those with the lowest efficiency values are 3, 5, and 8. When taking a closer look to these results, it may become noticeable that the fluids with the lowest efficiencies are the ones that are more viscous. Therefore, it can be said that the design pump doesn't have a great performance with viscous liquids.
In terms of the head, it can be seen that the value for this parameter decreases as the volumetric flow increases. It is also observable that the fluids that are more viscous have lower values for the total head. Similarly, water and fluids with the lowest values of viscosity are those with the highest head.
This makes sense due to the fact that the rotational speed was maintained constant, but mainly because with a greater volumetric flow, a higher resistance to the fluid is generated, causing the head to decrease. As we can see in the graph, fluids 3, 5, and 8 have a descending tendency of the brake power. This is due to that the B parameter of the algorithm gave a number higher than 40, which meant that we couldn't use this algorithm for these ones. However, we plotted them to corroborate this information, and we noticed that these fluids are the ones that have the higher viscosity and a higher Reynolds number.
In the table shown, can be seen the results for the Reynolds number. The fluids that were in the zone of transition were simulated as turbulent. Because it is a pure approximation,
it is observed that the head in the best efficiency point is greater when the Reynolds number reaches higher values, that is, for the less viscous liquids. The reason for this is that if a fluid is very viscous, by definition, it will have more resistance to flow, and as a result, friction forces will cause it to reach a smaller height. Taking into account the BEP, it can be said that the maximum head attained by the pump is 0.58 approximately.
To calculate the head in the shutoff, we used the line of tendency of the head when it was intercepted in the y-axis. Also, we can appreciate that the fluids with low viscosity and high Reynolds number have a higher head. As we can appreciate for the graphs of fluids 1, 4, and 7, they behave as we expected because the efficiency grows up to the best efficiency point and the head decreases when the caudal increases. When comparing the results of CFD and MATLAB for the head, we noticed that when the viscosity of the fluid we're working with is very similar to the water, it is very precise on the calculations. However, when it goes far away from the viscosity of the water, it's not as precise.
Also, it can be seen at the shutoff point that the values of the CFD simulation are higher than the MATLAB simulation, due to some problems that the Hydraulic Institute algorithm has to model viscous fluids with properties that are not similar for the water.
In summary, for the algorithm of the Hydraulic Institute, it can be noticed how this method was restricted by the B parameter, because for those fluids with a B greater than 40 and with a Reynolds number that was small, the results were incoherent, for example, presenting power that had trendline with a negative slope. As for the simulation in CFD, the results show that with a higher viscosity, a lower total head value was obtained and a bigger power was obtained as well. It was also proven that when the density increases with a constant viscosity, all values for the pump increase too. In contrast, both methods are useful for analyzing pump's performance, but the CFD simulation includes more fluids with coherent results than the algorithm. This can be due to the fact that the algorithm calculation is designed for water, so when a fluid has a similar value of density and viscosity to the water, the results are more accurate.